let's solve these logarithmic equations. All right, now remember, let's talk about what we've just finished with our last couple examples. In this problem here, we're looking at 6 times log base 2 of 4x minus 7 equal to 18. So the question is, what does x equal? With that said, I want to go ahead and look at rewriting it exponentially. It's my goal. With that said, I'm going to have to do a little bit of work first on this one. So before I can convert it over exponentially, I need to go ahead and use the power rule here. Let's go ahead and get rid of that coefficient. So let's apply the power rule here to help us to convert over. So that implies we got log base 2 of 4x minus 7 raised to the 6th power equal to 18. Well, now I can convert it. So in my logarithm, let's go ahead and rewrite it. So I'm going to rewrite exponentially. So that's my next step, to convert it. Convert over to a exponential equation. So remember our log definition. Log base a of x equal y if and only if a to the y power equal x. I want to go from here to there. So that implies 2 to the 18th power equal 4x minus 7 raised to the 6th power. Right? So again, using our definition of a logarithm. Now, with that said, right, we've got a statement here. We can go ahead and simplify. Now, what is 2 to the 18th power equal to 4x minus 7 raised to the 6th power? Let's go ahead and look at our calculator. What's 2 to the 18th power give us? We get 262,144. 262 144, 262, 144, equal to 4x minus 7 raised to 6. And if we're going to take this, we need to do the 6th root of both sides to solve for x. And as we do that, all right, what do we end up with? What is the 6th root? What is 262, 144 raised to the 1/6 power? So let's go ahead and check that out. All right, let's go ahead and raise it to a power of 1/6. I'm going to use my exponent. So we got 8. The 6th root of that, remember, 6th root, same thing as 1/6 power. So I went ahead and use the exponent. So that simplifies to 8 equal to 4x minus 7. And then we can go ahead and solve for x in our equation. We can go ahead and add the 7 over on both sides. So 15 equal 4x. We can divide out the 4 on both sides. And x is equal to 15/4. Right? And then we could check it. So we could always plug that back in and check. And if you plug it back in, log base 2 of 4 times 15/4. Right? That'll be 15. 15 minus 7 is 8. Log base 2 of 8 is 3. 6 times 3 is 18. So definitely can check that. Right? So sometimes it helps, right, to do a quick check step and check those out on there. So again, make sure you check your work if you're not sure of your answer. So again, I'm going to plug in my answer here real quick just to show you that work. 4 times x. So as we plug in x here, we got 15/4 minus 7, supposed to equal 18. Well, again, as we simplify that, that's log base 2. 4's cancel out, and that's 15 minus 7 equal to 18, which again, that's 6 times log base 2 of 8. And we all know what log base 2 of 8 equals. 2 cubes 8, so all this is equal to 3. And yeah, we get 18 equal to 18. Right, it checks. So again, you can take that time and check it. So again, that's a good one. Well, I used my power rule, rewrote it exponentially. Went ahead and solved it. Took the 6th root of both sides as we went there in that problem, and then used our calculator to help us a little bit. Let's go to the next example here in F. In F, let's see what x is. Now here's our log x term. Now first thing I want to do on this problem is let's go ahead and get the logarithms together. Right? We'll go ahead and get those together on one side. Right, so let's go ahead and put this natural log of 3. We'll move this 5 over to the other side. So I'm going to go ahead and subtract 5. Let's subtract the ln of 3 over here with it. So as we do that, we end up with the natural log of x plus 2 equal to 1, right, as we move those terms together. All right, somebody check me. We forgot our minus ln of 3 we moved over, equal to 1. And now I'm going to use the quotient rule. So again, we got a difference of logs. So what rule allows us to subtract logarithms? Quotient rule. So that's natural log of x plus 2 divided by 3 equal to 1. And then we can rewrite it. So now I'm ready to convert over. I'm going to rewrite exponentially. All right, so remember, what is our property? We've got what? Log base e. So this is a log base e logarithm. So we got e to the first power must equal x plus 2 over 3. So again, ln, if you need to, we can rewrite that as log base e. I'll put that in here, log base e. But there it is. So ln is log base e. So e to 1 power equal x plus 2 over 3. Well, with that said, we got a couple steps left to solve this. So we got e equal to x plus 2 over 3. Well, to get x by itself, let's go ahead and get rid of the 3. I'll go ahead and multiply both sides by 3. And with that, we got 3e equal to x plus 2. And then we can subtract our 2 over on both sides, and we'll have our answer. So what does x equal? X is equal to 3e minus 2. There's our solution, 3e minus 2. Right. And again, you can plug it in to check it, right, if you want to check that. And again, you go back to your original and plug in and simplify down, see if it equals, and it will. All right, let's go to another example. Example G. Now in G, we've got a couple of log x terms. All right, so I want to go ahead and work on getting these log x terms together. That'd be our first step. We need to combine those together on one side. All right, and then we can work on solving it. So let's go ahead and move this over. So we'll go ahead and add that over to the other side. So with that said, we're going to have a plus log base 6 of x plus 3 to move over here with the other logarithm. All right, and then we can go ahead and add the 1 over. We'll go ahead and add it over. I want to do it in the same step. We'll plus 1 on both sides. So with that said, rearranging our equation, we've got log base 6 of x plus 4 plus log base 6 of x plus 3 equal to 1. And then since we're adding logarithms, how do we do that? We apply the product rule. Log of m plus log of n is log of m times n. So x plus 4 times x plus 3 equal to 1. And now we're ready to rewrite it. So we want to rewrite exponentially. Ready to convert it. So we got the conversion to take place. Now with that said, we have 6 to the 1 power equal to x plus 4 times x plus 3. And let's go ahead and do the multiplication as we distribute. I got x times x, x squared. We've got x times 3, which is 3x. And then we'll go ahead and different color. We'll distribute the 4 through. 4 times x, 4x. 4 times 3 is 12. So right now our equation reads 6 equal to x squared plus 7x plus 12. As we subtract 6 over, what do we do with quadratic equations? All right, we set them equal to 0. So moving that over, we get x squared plus 7x plus 6 equals 0. And now we can solve this one easily. Let's factor. So every quadratic has 2 linear factors. And we got an x and x up front for the x squared term. We need a 1 and a 6 as we build a product. So that implies x plus 1 equals 0, or x plus 6 equals 0. So we got x equal negative 1, or x equal negative 6. Now you got to check for those solutions, make sure not extraneous solutions. Now if you check negative 1, you're okay. Well, I want to notice what happens if you plug in negative 6. So if I were to go back up here at the beginning and check, right, we got log base 6 of negative 6 plus 4. Well, we can stop real quick. We cannot take the log of a negative. That's an extraneous solution. Now, if we were to plug in negative 1, right, let's say we were checking it. So again, checking negative 6 didn't work. But if you check negative 1, we're okay. We get log base 6 of negative 1 plus 4 minus 1 equal to negative log base 6 of negative 1 plus 3. Well, as we simplify that, that's log base 6 of 3 minus 1 equal to negative log base 6 of 2. Now that's okay. We're not taking the log of a negative. And log base 6 of 3 minus 1, right, will equal negative log base 6 of 2. So you can check that. But we have one extraneous solution, so only one works. So our answer, x equal negative 1. So again, that's what we call an extraneous solution. And that one doesn't satisfy the given restriction. Let's move on. Let's go to the next one. So let's go ahead and solve for x here. So again, a couple of log x terms. Let's move them together. Let's go ahead and add that over. So we need to add log base 2 of x minus 6 over here to the other side of the equation. So if we do that, we get log base 2 of x minus 6 minus log base 2 of x plus 1 equal to 3. And then we can use our quotient rule. Our quotient rule will allow us to subtract the logarithms. Log of m minus log of n is log of m divided by n equal to 3. And then we're ready to rewrite exponentially. So that single log on one side. So we can go ahead and convert. So log base a of x equal y, that implies a to the y equal x as we convert over. So that implies 8 is equal to x minus 6 over x plus 1. Now, how do we solve the resulting equation? We've got a rational, so we'll go ahead and clear out the fraction. We'll multiply both sides by x plus 1. And as we do that, now what is 8 times x? 8 times 1, we get 8x plus 8 equal to x minus 6. And as we're solving for x, we're going to get the x terms together on one side. We're going to move the 8 over here to the other side, and that gives us what? 7x equal to negative 14. As we divide out our 7 on both sides, x equal negative 2. Well, x equal negative 2, right? What happens if you check? So I go in and check my answer. We quickly find out we got a problem, right? We get negative log base 2 of negative 2 plus 1. Well, that's negative log base 2 of negative 1, which we can't do. Undefined, right? Don't need to go any further. Can't take log of negative. So we have no solution, right? As we're looking at this equation, there's no answer. We only have one possible answer from that rational equation, right? And again, it did not check as we looked at simplifying that and plugging it in. All right, got one more. Let's look at example I and see if we can solve this one. So same thing, let's go ahead and move that term over. We got to add the log of x plus 15 over to the other side. So I've got the log of x plus the log of x plus 15 equal to 2. And we know since we're adding, we'll use the product rule. And the product rule says log of m plus the log of n is equal to log of m times n. So we're going to multiply these together. So again, this is log base 10, right, of that product. So there's the product. Let's go ahead and multiply that and simplify. So we end up with log base 10 of x squared plus 15x. So we do the product equal to 2. And then we're ready to convert it. So we want to rewrite it exponentially. So let's go ahead and convert exponentially. Log base a of x equal y. So 10a to the y power, 10 to the second power, must equal x squared plus 15x, which means 100 equal x squared plus 15x. And as we're solving again a quadratic equation results, we need to set it equal to 0 to solve it. So we end up with x squared plus 15x minus 100 equal to 0. And now we got to find factors of 100. Well, what factors of 100 will work together to make 15? We know 5 times 20 is 100, right? We can use that to cofactor. So as we build our two linear factors, which our quadratic has, we need an x and x up front for the x squared term. And then we're going to need a, what? Plus 20. We need 15, 20 minus 5, and a minus 5. So there are two linear factors. Of course, with that, we use our zero factor property. X plus 20 can equal 0, or x minus 5 can equal 0, which implies x equal negative 20, or x equal 5. Now, as we're checking, all right, I'm concerned about this one. All right, what happens with our check step? So if we're to plug that in, I quickly see there's no way negative 20 is going to be an answer. We get the log of negative 20, it can't happen. Now 5, we're okay. Right, we would get the log of 5 equal to 2 minus the log of 5 plus 15, which is log of 20. And that will check. So of these solutions, we have one extraneous solution. So we have one answer, that solution being 5. So those are logarithmic equations, right? Using our properties to help us, right? And using our log definition. Remember, logs are exponents. So we can convert them over exponentially.